Cool. So, let's go ahead and begin. So, when last we spoke, we talked about just using logarithms to solve some exponential equations. And we had left off with here's some closing steps and approaches to solve one of these. Anyone go through and take one of these two approaches and wind up solving this exponential equation down to a single answer? Cool, then let's do it. So we had two mindsets we mentioned. So either you can take 3 to the x to the power 2, and rewrite that as 3 to the 2x, leave 8 alone. And let's just try to solve that, and we'll see what ideas we need as we go. If there's an equation you want to solve, what seems like a good idea? Yeah. Let's turn it into a logarithmic equation. What happens when you turn that into a logarithm?
Log 3, 8 equals 2x.
Log base 3 of 8 equals 2x. Great. And you know what? I'm even going to put that rule on the board because we're going to use that a lot. Whenever you see an equation in exponential form, that pen is dead. You can put it into log form as log base b of y equals x. All right, so we use that in this step. Does that look like we're closer to having x solved for? I think so. There's only one thing left. What do you need to do to finish that off? Get x by itself. How do you do that? Divide by 2. So it looks like I'm getting x equals 1/2 log base 3 of 8. Cool. Does that feel pretty all right? We also started on a different track doing something similar to solve the same equation. Well, here's another mindset you could have. There's only one x on the left-hand side. So you can just imagine undoing everything you do on the left-hand side in the opposite order, and then you'll get x on its own. Yeah?
I was just going to ask, to do the logs in the calculator, would it be log 8 divided by log 3?
Yeah, so if you have a calculator, chances are, what calculator are you using?
I'm using a TI-84.
Cool, you can definitely enter in an arbitrary log. I know that the TI-84 can do that.
Okay.
Maybe I don't know how, but I know that it can. In fact, how many other people here are TI-84 users? Leave your hand up if you know how to enter an arbitrary base in your log in a TI-84. Cool, so I know it can be done, and there are people you might talk to. Also, the manuals available. But yeah, if you don't want to learn how to do that, it's just 1/2 log 8 over log 3, and in fact, as long as we're talking about that, what is that? Give me a decimal approximation. 1.89. Cool. Well, we had another approach here that started by saying, well, let's undo that square with the square root. And whenever you undo a square with the square root, you get a plus or minus showing up. Does that look like an equation you could also do something similar to solve? I think so. What would you want to do to solve this? Well, it's, yeah.
Log base 3 of plus minus square root 8.
Yeah.
X.
Cool. So just put it in log form. You'll get log base 3 of root 8, or x equals log base 3 of negative root 8. And that's kind of weird, right? We only got one answer. This seems to be saying there are two answers. So something's got to be off. Either we lost information here and we should have gotten two answers, or one of those is fake. Well, what's the deal? Any thoughts?
My calculator says no negative in the log.
Cool.
Or conservative, I'm not sure which.
Well, let's check it out. Well, there's not a negative in the square root, so that can't be the problem.
Well, I
But-
put negative square root thing and that just says not an answer.
Yeah, because there's a negative inside of a log. Let's flash back to this picture of the graph of a logarithm. What's the domain of that function? How do you read off the domain from a graph?
X, all the X values.
All the x values. So by looking at this graph, what's the domain of that function?
0 to infinity.
Things bigger than 0, so positive things. That positive? Cool. So that answer is not actually an answer. I guess it is telling you that there's something like imaginary going on there. But let's backtrack even further. That's 3 to the x equals plus or minus root 8. Is the square root of 3, is 3 to the x ever equal to the square root of 8? Nah, 3 to the x can only be positive. So I guess here are 2 lessons here. Well, let's check one more thing. So we've eliminated this as an option. This is not actually a solution. What decimal approximation do you get for log base 3 of root 8? Excellent. So those 2 things agree. That's good. That tells you that those 2 answers are probably at least consistent. I guess that also means that there's like an identity we're seeing. It looks like the square root of 8 inside of log base 3 instead is the same as taking the log base 3 and then multiplying by a half. That's kind of neat. We'll see that more formally, hopefully by the end of today. Let's do one more example. So let's remember earlier, like the start of the lecture on exponentials. Like we talked about a sample of americium 240, which is this radioactive element. Anyone here like a chemist or physicist? I'm wondering if anyone here can correct my pronunciation of americium.
Oh, you're right.
Oh, that's right? Oh, it seems like such an awkward thing to say. Yeah, fair enough. We modeled its quantity at any given time. With the initial quantity times, well, how many times do you divide by 2? Well, you count how many half-lives have gone by. Well, it's t over 2, where t is measured in days, because the half-life is 2 days. And you multiply by 1/2 that many times. So if you start with 1 kilogram, and you want to run an experiment which requires the sample to contain at least 3 grams, let's figure out how long you have to run this experiment. So let's try to unpack that. What equation do you need to solve to do this? What are you looking to figure out if you want to address this? Yeah, you want to solve for t because you want to know how long until. So it looks like we need to solve something for t. What do we need to solve for t?
What t-value returns the value of 3?
Yeah, what t-value returns a total of 3 grams? So p of t equals 3 grams. Well, I have a formula for p of t. It is initial mass, which is 1 kilogram, equal to times 1/2 to the t over 2 equals 3 grams. That look like something you could solve for t? Hopefully. Before you do any algebra there's like one thing you have to do first.
Convert kilograms to grams?
Yeah, let's get the units to be consistent. And either kilograms to grams or grams to kilograms, doesn't matter which. Maybe convert the kilograms to grams is a good thing to do, because maybe it's easier to write down 1,000 than to divide by 1,000. So,
1,000 grams times 1/2 to the t/2 equals 3 grams.
Yeah, okay. There's an equation to solve. How would you want to solve it?
Honestly, school I'm seeing is to divide plus our thing with and I'm wondering if there is something better than
Well, I mean, let's see. What's the order of things you do to t? You start with t, then you divide by 2. Then you put that in an exponent, because exponentiation happens before multiplication. Then you multiply that by 1,000 grams. So multiplying by 1,000 grams is the last thing you do. So I think division by 1,000 grams is a great thing to do first. So let's do that. Divide by 1,000 grams. I'm going to get 1/2 to the power t/2, where t is measured in days, and this 2 is actually like 2 days, equals 3 grams divided by 1,000 grams. And the whole point of doing that is the grams are now going to cancel. So 3/1,000. If you were doing this, would you leave that as 3/1,000 or rewrite that as 0.003? Decimal? Fraction. Cool. I don't care which. I'll put it as the decimal since that seems to be the preference. If you want to leave it as a fraction, leave it as a fraction. And notice, no more units. That's just 0.003. All right. So now I see 1/2 raised to the t/2 is equal to 0.003.
Yeah.
Isn't that an exponential form now?
That's an exponential form now. And all the unknowns are inside of the exponent? Oh, cool. So we can use that. Let's use that.
When you put that into logarithmic form, what do you get? Well, I'll start. Log.
0.003. And all that is equal to t/2.
Nice. Cool. All right, the base is the base. The thing inside the parentheses is the thing that used to be on its own. The thing in the exponent is now on the other side. Yeah.
All right. We want to solve that for t. What's still left to do? Oh, is there something wrong?
No. Could you also write that as t/2 log 1/2 equals log 3, or log 3/3?
Gesundheit.
Yeah.
Yeah, so I think what you're saying is like use the change of base formula.
Yeah, pretty much.
Yeah, you definitely could. So if you're one of the people who's like stuck using a calculator that like doesn't let you walk in a different base, which maybe you are, you could rewrite this as the log of your base, your favorite base, 0.003, divided by the log of 1/2 equals t/2. Like that?
Yeah.
Yeah. Cool. And in the meantime, what do I still need to do to get t on its own?
Multiply both sides by 2.
Cool. I'm actually just going to use the fact that I can erase because my space management has been like really bad. And that's in days, I guess. Just have to remember that. Cool. So let's like figure that out. So what is that?
Like 8.38. Right now.
Is that with the 2?
I thought it was log 0.03 divided by log 1/2.
Yeah. All that's great. And then multiply that by 2.
Oh, yeah. So it's like 16 down 76.
And t is measured in, oh no, t is measured in hours, not days. What am I doing? Cool. So you have about 16.76 hours, so 16 hours, 45 minutes-ish to complete this experiment. And as long as we're making observations about this, let's see. So there's some things you see here. Exponentials grow really quickly. Or I guess in this case, decay really quickly. To go all the way from 1,000 grams down to 3 grams only took 16 hours. So it's decaying to 0 really quickly. Logarithms also grow really slowly. So even though 0.003, well, that's like really close to 0, right? So I should be getting close to that vortical asymptote you know the logarithms have. But the result of that log, well, I guess this was divided by 2, is only like 8. So even though you're getting really close to that vortical asymptote, the y value is not that big yet. Cool. Nice. So the last thing I want to do in this particular packet before we start in on something else is I want to make some analyses about just logarithms in general. And the way I want to do this is let's just remember what graphs of logarithms look like. And to do that, I guess we need to remember what graphs of exponentials look like. So what does the graph of an exponential function look like? Yeah, like for very negative powers, it's close to 0, then it starts carving up. It goes through the y-axis at some point that we'll label, and then it starts growing real quick. What's b to the 0? 1. And there's assumption in this. What types of values for b result in a graph that looks like that? Positive? And more than just positive, bigger than 1. Because, right, like 1/2 to the x, it'll get small instead of getting big. So this is in the case that b is bigger than 1. I won't allow negative bases in my exponential functions at all, because if you try to figure out what like negative pi to the x should look like, you'll wind up needing to compute like negative pi to the 1/2. That's the square root of a negative. That'll be imaginary. Then you also need to figure out like negative pi to the like e power. That'll be all kinds of complex, like literally complex. You'll need to think about complex numbers to make sense of it. So we just won't. When b is between 0 and 1, though, its graph looks like that. I'll never think about the base being 0 and think of that as a function, because then I'd need to think about 0 to the 0, or 0 to a negative number, which would be all kinds of bad. I guess there's one more number then. What does 1 to the x look like?
Straight line.
Straight line. Any power of 1 is 1. I guess I'll leave that there then. There's 1 to the x. So let's see, logarithms are the inverses to these. So let's graph the inverses. How do you get the graph of an inverse function from the graph of a function?
Switch these lines.
Switch the x and y's. So right now the only labeled point is this point here at 1, 0. Nope, 0, 1. Where's that going to go when you swap the x and y?
1, 0.
1, 0. There's this point here at 1, 0. The pink graph, when b is bigger than 0, tells you that the log base b of x, its graph will look like that, as long as b is bigger than 0. No, b is bigger than 1. Come now. When b is between 0 and 1, the graph of a log will look like this. What about when b is equal to 1? What will the graph look like then? Yeah, vertical line, except that's a trick question. That's not a function. You can't talk about the log base 1. It's not a function. So I won't even try. So let's summarize some things. So for what bases are you allowed to talk about logarithms? What values are allowed in that base? Positive. And one more rule.
Can't be 1.
Can't be 1. Once you do have a valid base, though, let's read off the domain. What's the domain of those functions? 0 to infinity. Or if you want it as an inequality, x has to be bigger than 0. What's the range? Yeah, everything, right? You look at what y values you see, it's everything. X-intercept at 1, 0. Any particle asymptotes? X equals 0. And that's for both of the options of log. They just have like opposite direction particle asymptotes. Horizontal asymptotes.
Would it be like B?
Nah, they just keep growing, right? They'll grow slowly, but it'll make it past B eventually. Right? And maybe to see that like it takes a while because these things grow real slow like. Give me a choice of B to use. 7. That was the one I heard loudest. Long. There's the graph of log base 7 of x. And let's see. Let's draw that horizontal asymptote at y equals 7. This will take a while for it to get there. I think I want to adjust it this way. So let's look a long ways out on the x-axis. Does it make it past that eventually? Took a while though, didn't it? And that it looks like it took me till almost 1 million before I passed a y value of 7. So it does keep growing without bound. It just takes a while. Logarithms grow without ceasing, but they get real slow. Cool. That feel pretty all right? Nice. One last thing I want to do in this particular packet before we start in on doing some algebra with logarithms. Let's combine this idea of domain with like complicated stuff inside of a log. So let's suppose I asked you to compute the domain of log base 2 of 3x minus 4. Based on what happened in the previous page, let's remember how you always think about domains. You think about domains by thinking about like what can go wrong in this formula. And let's be real slow about it. 3x, is there anything you cannot multiply by 3? Nope, so that's fine. Anything you cannot subtract fourth one? Nope, that's fine. Is there anything you cannot plug into a logarithm? What things? Negative, or 0 is bad too. So to get this domain, you need, right, for each of these I want to compute the domain. It's on the previous page, this instruction. Compute the domain. So to get this domain, it looks like I need to solve 3x minus 4 bigger than 0. Oh, is that like a super easy inequality to solve? In fact, do I need to do anything? I can if people want. Otherwise, what's the solution? X is bigger than 4 thirds? Yeah, all right, so this is like nice in that I can add 4 to the other side. That doesn't screw up the inequality. I can divide by 3. That doesn't screw up the inequality. So I guess that's 4 over 3 on to infinity. That feel pretty good? Let's see, there's some others in this list, like there's some more functions to compute the domain of. I think I'd like to spend in-class time on like one of them and then maybe some time on another if we want to like talk about another one at all. So, if here are the options to talk about, A, B, and C, which one would you like to talk about together? A? B? C? Cool. I think the B's have the majority, and there were a few C's. So let's talk through B in detail. Let's take a moment and at least write down what inequality do you need to solve to do this first one.
From x squared and 0.
Nice. And that's an inequality you know how to solve, right? You'd solve the equality, then check some sample points, and then interpret your result. Same thing here. If you want to compute the domain of this thing, what inequality do you need to solve? Cool. So, in order to solve that, there's the thing I need to solve. What was like the general process we used to solve rational inequalities? Solve equality is like step 1. Then? Yeah, there's one step you're skipping that's important. You need to check for vortical asymptotes. Vortical asymptotes can screw up an inequality too. So when you want to solve an inequality, solve equality, then figure out places where something bad happens, and then check some sample points between. So, step 1. 1 plus x over 1 minus x equals 0. Oh, that actually looks like I've rigged this example, so the actual algebra is not the difficult part, right? That looks like something you know how to solve? Should I do any of the work? I'm perfectly happy to. Cool, then I will. Those of you who are saying, no, you must have an idea. You want to solve that, how do you do it?
Multiply both sides by 1 minus x.
That seems like a reasonable plan. Let's multiply both sides by the denominator. So, 1 plus x is equal to 0 multiplied by 1 minus x. Oh, and what's 0 times anything? Cool, so what do I have? I have 1 plus x equals 0. So, what's x? Very good. I think in the notes I called this step 1b, find vortical asymptotes. Find vortical asymptotes. And sometimes that's easy, sometimes it's not. Is this one where you can just read off the vortical asymptotes? Yeah, where are they?
X equals 1.
Just x equals 1? Yeah, set the denominator equal to 0. So you set 1 minus x equal to 0, add x to the other side, x equals 1. Vortical asymptote at x equals 1. And maybe I'll even do this quick check. So like x equals negative 1 and x equals positive 1. Those will be like the end points of the solution. So the solution will be like some of the intervals with those endpoints. Let's check if those are included first. X equals negative 1. Include or exclude? I hear an exclude. Anyone want to say include? Cool, yeah, I agree. Why exclude?
Because because 1 plus negative 1 is 0, and the log can't get a log of 0.
Nice. If you plug in x equals negative 1, you'll get 1. You'll get a 0 in here. Log of 0 is forbidden. Alternately, it's because you needed to solve strictly bigger than. And whenever you want to solve a strictly bigger than, well, this came from equality. What about x equals 1? Include or exclude? Exclude. Why exclude? Vortical asymptote. There's a division by 0 error. So I guess when you plug in negative 1, the calculator would probably say you can't have a 0 and a log is the error. And when you plug in 1, you get a division by 0 error. Depending on how informative the error messages your calculator gives you are. All right, so now we have to check some sample points. So let's see, there's negative 1, there's 1. Let's plug in some sample points. Let's see if we can even plug them in without like writing very much. Give me a sample point that is to the left of negative 1.
Negative 5.
Negative 5. Let's plug negative 5 into this ratio and see if we get something positive. When you plug in negative 5, the numerator is positive or negative? Negative. When you plug in negative 5, the denominator is positive or negative? Positive. Because 1 minus minus 5 is positive. I don't care exactly what they are. When you divide a negative by a positive, you get a negative. Cool. So include or exclude? Cool. So that was like without writing anything, but that went pretty okay? Exclude. Give me a sample value in between negative 1 and 1. 0. When you plug in 0, include or exclude? Awesome. In fact, I think I saw some of this going on, so I think you even get this to be equal to 1. That's cool. So I guess that means log of 1 is 0, so when you plug in x equals 0 to the whole function, you get a total output value of 0. That's good to know. Something bigger than 1. Include or exclude? Cool. So what's the domain? Domain is the interval from negative 1 to 1. How should I decorate those endpoints? Cool, because they're both supposed to be excluded. Neato. That feel pretty good? All right. So, all of the things you remember about solving inequalities, you need to use those if you want to find the domain of a logarithmic function. And let's We'll write down the inequality you need for this last one and see what more we want to talk about. There's a function whose domain you want. What inequality do you need to solve?
If the value of x is greater than.
Is it? Be careful. Yeah, what's the absolute value of 0? Is 0 bigger than 0? If I plug in anything other than 0, is the absolute value always bigger than 0? Cool. So I guess we don't even need to do any algebra. Just absolute value is only 0 at x equals 0. So it looks like the domain is all real numbers but 0. Oh, cool. How do people feel about that? That go pretty okay? Yeah.
So you can never have 0 inside of like a log function?
That's right.
Okay, because it ends up not being a function, right? Is that why?
Because of the vertical asymptote that the log has. So there's the graph of the logarithm.
Yeah.
At an x value of 0, I don't see a y value.
Oh, okay, I see.
And if you want to like keep backtracking that further, that's like asking what x value results in an exponential being 0, and that definitely doesn't happen.
Right.
So I guess like maybe you'd want to say like the log of 0 is plus infinity or minus infinity, but like you shouldn't say that because really you should describe that as a limit. Cool. People feel pretty good? Yes. And maybe I should just linger here for a few moments. So the last thing on this page, let's just write down what this thing is going to have you do. So there's the graph of the natural log of x. Oh, cool. Let's just talk through in words. How would you then graph this function? This is like a super flash from the past. That minus 1, what does it do to the graph? Shifts it down 1. What does that plus 1 do to the graph? Left 1. Things inside the parentheses do the opposite of what you expect. What does that 2 next to the x do to the graph? Compresses by a factor of 2. Right. Anything inside the parentheses does the opposite of what you expect. And was that the right order to do them in? I think it was, right? So first you would deal with like anything multiplied out front, then you do the shift, and then the scaling next to the x. Cool. So I'm not going to do that. Think about graphs of functions. There are a few web books where you'll think about graphs of logarithms after transformations. Instead, let's do some logarithmic laws. So let's start by remembering, like, exponentials have like some nice algebraic laws they follow, right? Like, if I do b to the x to the y, what's that the same as? What if I do b to the x plus y? How could you rewrite that? Yeah. So what's the takeaway here? If you like add numbers together inside of the exponent, that's the same as multiplying the exponents together. Logarithms are like the opposite of exponentials. So they should satisfy these same algebraic rules just like in reverse. So I won't try to go through like the proofs of why these happen. If you want to go through those, like the philosophy is just take that rule and write it backwards. There's an extra credit in which you can talk through the details. Let's use this idea to like just read off some things. And I guess the first couple are like things you already know. What's the log of 1? 0. What's the log base b of b? That one's 1. What's the log base b of x times y? Any thoughts? Yeah.
Do log b x plus log b of y.
That seems pretty intuitive, right? Addition inside of the exponent became multiplication outside. Log should do like the opposite. So multiplication inside should become addition outside. So log base b of xy is the same thing as log base b of x plus log base b of y. And there's one like really important application of that that's maybe less important now than it was like 50 years ago. I'm only 40, so like, you know. How many people have ever used a slide rule? A slide rule. How many people have ever seen a slide rule? How many people are aware of what a slide rule is? Okay, okay. Those numbers have been tracking down since starting my teaching career.
Can we see the picture?
Yeah.
Yeah, sure. I should have brought my slide rule with me. I have my dad's old slide rule at home. Yeah. So what's a slide rule? This is a really dangerous thing to do. Just like a Google search in class in an audience. Who knows what I'll find? Not slide. Yeah. So what's a slide rule? It's like a thing that's like 3 rulers attached together. The middle one slides across. And the point is you can use that to do addition. Because if you want to know what the sum of 2 numbers is, you figure out what you're adding to what. That tells you how far to slide. Then you see where something points at the end. And how precise your slide rule is basically how big is your slide rule. You can get more precision if you can like look at it closer. So it's like a totally mechanical adding machine. And that's all it can do, it adds. So what's the point of like this and how it connects to this logarithm rule? Let's suppose that you have a slide rule so you can add numbers and you're really good at that. But you want to multiply together 2 really big numbers together. So if you want to do that, here's what you do. You take those 2 big numbers, you compute their logarithms. And in order to compute their logarithms, well, you have yourself a logarithm lookup table, which is a tome that you have around with you whenever you want to do computation, in which you look up what the log of those 2 numbers is. Then you use your slide rule to add those 2 numbers together. Now you know what the log of the sum is. That means you know what the log of the product is. Well, that means you need something that like undoes the log. So you take out your inverse log transform book, which really is what they call it, even though that's just like an exponential function, to figure out what the exponential of the thing that you know x times y is. Oh, hey, you just did multiplication by just doing addition. That's a neat trick. Anyway, carrying on from there, that's not something anyone does anymore, though, is it? And that's not how a calculator does addition either, or multiplication. Calculator does something else, more like what you do with digits. What about division? If multiplication became addition, what should division become? That certainly seems intuitive, right? And I'm not going to try to like prove any of these things today. That's an extra credit.
Log B of B is, oh, never mind.
Yeah, log b of b is 1.
I just heard a B.
No, that's fair. It was 1, but it was casting a shadow. There was like perspective.
I see.
That's what it was. Right. Yeah.
Why are you parentheses around the x and not the y?
No reason. Yeah, right. Like sometimes like one is lazy and you just don't write the parentheses, and then you just have to trust that the reader knows that that's a function, so it needs an input. So the next thing should be the input. But one shouldn't be too lazy. Yeah.
So if we put in the words like why this is, we get some extra credit?
Section 5.3.1 in the notes is going to guide you through the proof. You'll go through those, and then you'll put that into WADS, and then come talk to me. Or if you can like put a reason into WADS that's independent of that, yeah, you can talk through that reasoning to me too. Cool. And if you're someone who like just doesn't have the notes, because I don't think you have the notes, you've never had them, they're available online, so there are PDFs up there. So if multiplication became addition, let's think about what exponentiation should do. And let's maybe do it by thinking about like what exponentiation means. Like, what does x to the 5th mean?
X times X times X times X times X.
I lost count. You probably said it 5 times. So, well, let's think about what that means about log of x to the 5th. That would be the log of x, 2, 3, 4, 5, with multiplications between each. Oh, each of those is going to become addition, right? Oh, cool. So that's like log x plus log x 5 times. Oh, that's the same as just 5 log x. So it looks like this 5 could pull out front as a multiple. Think we could do that for any exponent? Yeah. Log base b of x to the y is the same thing as y times log base b of x.
And there are 2 more important rules that are worth having. The first is one we've used a few times is like a computational crutch, and that's the change of base formula. Whenever you have a log that's in a base you don't like, either because like you just have a bunch of different bases in your problem and that gets annoying, so you should make them all be the same, or you're in a situation where like you want to use a calculator and it's not the base you want, you can change base. Log base a of x is equal to the log base b of x divided by the log base b of a. And this is true independent of what this b is. That base b can be anything you want. Any, let's say, legal base. Well, you better not be using this formula with b equals 1, for example. If you use it with b equals a negative, depending on exactly what your calculator does, it might spit out like a reasonable result. But it might spit out a result that's like off by a multiple of 2 pi I. It turns out that's like a weirdness that can happen when you plug in logs and negatives. Oh, yeah, I'm doing okay at the time. I think I want to do like one thing with the rest of today. Change of base formula for exponentials. A to the x is the same thing as b to the x times log base b of a. So if you want to walk with your favorite base, you can, at the cost of multiplying by something in the exponent. And that's a useful rule, like once you have a single base that you really prefer your exponents have. That's a rule that's worth knowing. So let's use this to solve an equation. There's an equation I would like to solve. So let's talk through like a plan of attack in how to solve that. I see like 2 logs on that side. Do I need to see 2 logs on that side? Would it be nicer if I only saw 1 log on that side? Yeah, because then I could use the changing from log form to exponential form. So let's use that.
How can I rewrite the left-hand side so there's only 1 logarithm? Yeah.
Log base 3 of x squared plus 8x.
Nice. And I'm going to break that out into 2 steps. X times x plus 8, because the addition becomes multiplication, and then you can distribute that out. Log base 3 of x squared plus 8x equals 2. All right. So now that we have only 1 log, what's a good trick? Let's see. Put it in exponential form, because right now all the unknowns are inside of the log. If I put it in exponential form, then all the unknowns will just be on their own. So I think that'll make my life better. Let's see what happens when you do. What's the base? To the power equals
X squared plus 8.
x squared plus 8x, yeah.
Yes.
Nice. That look like a better equation? In fact, does that look like an equation that you just know how to solve? Yeah, it's like quadratic, right? So I guess get everything onto the same side. Maybe it factors. Maybe you have to use the quadratic formula. 3 squared is 9, not 8. if you think too quickly, you'll wind up swapping the 3 and the 2, and you'll put an 8 there instead of a 3. I didn't this time, but I'm sure I will at some point. X squared plus 8x minus 9 equals 0. Let's see, that's like a quadratic equation. Does it factor?
Yeah.
Cool. What are the factors?
Positive 9 minus 1.
Positive 9 minus 1. By which you mean x plus 9 and x minus 1. And that's set equal to 0. Cool. So what are the solutions?
X equals -9 and x equals 1.
Nice. And it turns out that's incorrect. There's something wrong that happened.
No negative.
Yeah, like there's a domain issue. And let's see that there's a domain issue by like graphing. Right, if those are solutions, we should be able to graph this equation and like see two solutions. So let's graph log base 3 of x plus log base 3 of x plus 8. We get what we get. And now let's also graph y equals 2 and get a more reasonable. Oh, how many solutions does this look like it has? Just the one. It looks like it's at 1, so x equals 1 looks okay. And explicitly, yeah, there's nothing at x equals 9. So here's the point. Whenever you solve an equation using these logarithm laws, you do algebra. Whenever you do algebra, you might change the domain. And in fact, let's see that we did change the domain. Let's compute the domain of this function. Domain of log 3x plus log 3x plus 8. Well, I see a thing inside of a log right there. So what can you tell me that x has to be?
Greater than 0.
Greater than 0. I also see log base 3 of x plus 8. So what inequality does that tell you?
X plus 8 greater than 0.
Cool. And that one we can solve. X is bigger than negative 8. Is 1 both bigger than 0 and bigger than negative 8? Cool. So 1 is in the domain. Is negative 9 bigger than 8? It's also not bigger than negative 8. So this is like doubly not in the domain. So here is the thing to remember. You can go and solve a logarithmic equation. At the end, make sure that you check your answers are in the domain. And let's even see where the domain changed. So you can't plug x equals 9 into this expression. Yeah.
For the log 3 of x, why does x was not the main x?
Because I got that 8 confused. I was trying to do things too quickly without reading. So let's just see where the domain changed. That one, x had to be positive for this expression to make sense. Ooh, but notice when you plug negative 9 into this next expression, I see negative 9 times negative 1. Oh, a double negative becomes a positive. So somehow, since like negative 9 was not in the domain twice, it became in the domain after you did this bit of algebra. So I guess the payoff is algebra can change domain. So whenever you do a bunch of algebra to find a solution, go back and check that it's still in the domain. And that's especially true with logarithms. All right. I hope everyone has a good weekend. There's homework due tonight. And I think like kind of a bit of homework. There were like 2 open-endeds.
Yeah.
Yeah. And 3 workbooks. Thank you. Yeah, thank you.